Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi and today we are going to talk on module with the topic Nonlinear Dielectric and this is under the paper Ceramics. So after completion of this module, the students will be able to understand the distinction between ferroelectric, piezoelectric and pyroelectric materials. Further, we will be able to understand the fundamentals of ferroelectricity. Moreover, we will be discussing about ferroelectric switching. So before moving further, let us discuss about some basics of ferroelectric and piezoelectric materials. So far we have discussed linear dielectrics in which the dielectric constant increases linearly with the applied field, which is accompanied by the increase in polarization depending upon the presence of polarization mechanisms in the materials. So there are some special classes of dielectric materials which not only show above properties but also have very large dielectric constants. So these show some special effects according to which they are categorized into various categories. So the first is the coupling of strain and the electric field, which is known as piezoelectric ceramics. The second is temperature dependence of the polarization, means if we are increasing the temperature, the polarization is changing according to the temperature. So such type of materials are pyroelectric materials or pyroelectric ceramics. And the third thing is the presence of large polarization in the presence of electric field, that is the spontaneous polarization. So in this case, the large polarization arises when we are not applying any electric field. So when we are switching off the electric field, the polarization is still present. So such ceramics are known as ferroelectric ceramics. So most of these materials depends on the oxides which we are choosing. And as you can very well understand now, these properties will be greatly affected by the defect chemistry and the process variables. Like if it depends how we are processing the ceramics, it completely depends on the properties as well. So the presence of these features make these materials extremely useful for a variety of applications such as sensors, actuators, transducers, temperature detectors, imaging, permanent data storage and so on. So such type of nonlinear dielectric materials have wide range of applications and it is incomplete, the technology is incomplete without them. So in the following section, we will have a brief look at these properties with some examples and we will be taking all these ceramics one by one and will try to understand them. Classification based on crystal classes. So out of total 32 crystal point groups, the 21 are non-centrosymmetric. So students, these all the groups are tabulated in this table. So 21 are non-centrosymmetric, that is the crystals not having a center of symmetry. The term centrosymmetric refers to a space group which contains an inversion center as one of its symmetry elements, that is, for every point XYZ in the unit cell, there is an indistinguishable point -x, -y and -z. So the various crystal classes are cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, triclinic, and accordingly the point groups are also mentioned. So the total number of groups which are centrosymmetric point groups are 11 and non-centrosymmetric polar groups are 10 and non-polar are 11. Out of these 21 point groups, except group 4, 3, 2 crystals containing all other point groups exhibit piezoelectric effect. That is, upon application of an electric field, they exhibit strain, or upon application of an external stress, charges develop on the faces of a crystal, resulting in an induced electric field. Out of these 20 non-centrosymmetric point groups, 10 belonging to a polar crystals, that is crystals which possesses a unique polar axis, an axis showing different properties at the two ends. So these crystals can be spontaneously polarized, and polarization can be compensated through external or internal conductivity or twinning of domain formations. So the spontaneous polarization depends upon the temperature. So students, you can see a schematic showing the classification of piezo, pyro and ferroelectrics. Consequently, if a change in temperature imposed, an electric charge is developed on the faces of the crystal perpendicular to the polar axis. This is called pyroelectric effect. All 10 classes of polar crystal which we have discussed previously are pyroelectrics, and in some of these polar non-centrosymmetric crystals, the polarization along the polar axis can be reversed by reversing the polarity of the electric field. Such crystals are called ferroelectrics, that is, these are spontaneously polarized materials with reversible polarization. So by default, all ferroelectric materials are simultaneously pyroelectric and piezoelectric. Similarly, all pyroelectric materials are by default piezoelectric, but not all of them are ferroelectric, which can be seen in this schematic. Ferroelectric ceramics. Ferroelectric effect was first observed in Rochelle salt by a scientist, that is Roger Vallecid, in 1921. Afterwards, for years, the discovery didn't raise much excitement, possibly due to World War. However, a few decades, a renewed technological interest lead to much more extensive studies and a better understanding. In the subsequent years, many materials were discovered and were of technological interest as they were employed into a variety of applications, and among various categories of ferroelectric materials, following stand out either due to the interest in a structure or in the properties. So the examples are triglycerine sulfate and isomorphous materials, potassium dihydrogen phosphate and isomorphous materials, barium titanate and other perovskite structures compound such as KNbO3, PbTiO3, etc. Next are the complex oxides such as Orwellis compounds, Rochelle salts and similar compounds, and ferroelectric sulfates. So among various perovskite related compounds have been studied most, primarily due to their excited properties and reasonably high transition temperatures, making them attractive for various applications. So students, let us discuss the thermodynamic and structural features of such materials. So the first property is permanent dipole moment and polarization. These materials consist of net permanent dipole moment, that is finite vector sum of dipole moment even in the absence of electric field. This requires material to be non-centrosymmetric, whereas the dipole moment would be forced to be zero in a centrosymmetric material due to symmetry considerations. On top of this, there must be a spontaneous polarization, as well as, which means a center of positive and negative charges in a crystal would never be same. So students, you can see the structure of a cubic and tetragonal perovskites with dipole moment represented by an arrow due to the movement of central B ion up or down along C axis. So in this figure, a crystal structure of perovskite material such as BaTiO3 is shown. Here in cubic structure, the dipole is 0, while in tetragonal structure, that is B figure, the dipole moment is finite. And the displaced position of the central atom is the energetically stable position, that is the free energy is minimum. When this kind of ferroelectric material is switched, that is subject to a bipolar electric field, it exhibits a polarization versus electric field, which you can see in this figure. You can see that there is finite polarization in the absence of electric field, that is two equal and opposite values, that is plus PR or minus ER, also called remnant polarization. These two values can be connected with the position of central atom in the octahedra in the figure shown. So when you apply a field in direction, the central atom moves up with respect to oxygen octahedra, and when you change the polarity, it comes down in the opposite direction. Principle of ferroelectricity, that is energetics. The movement of central atom in the above structure, which we have discussed earlier in terms of energy diagram, is shown in this slide. So you can see the potential energy well on the left hand side and a crystal structure for AbO3 on the right hand side. This situation can be explained in terms of potential energy between two adjacent low energy sites. There are two equilibrium positions in which a B ion can stay but no change from one state to another, and energy must be provided to overcome an energy barrier, that is delta E. These energy wells further tilt to left or right depending upon the polarity of electric field, that is in the non-zero field state, making one configuration more stable than one another. However, a coercive field, which is the field required to bring the polarization back to zero, is needed when we switch to other direction of the field. So the ferroelectric materials follow the Curie-Weiss law, which is expressed as eta or xi is equal to 3 Tc by T minus Tc, and it is also equal to n alpha by epsilon naught divided by 1 minus n alpha upon 3 epsilon naught. So here n is the number of dipoles per unit volume of the material, alpha is the dipolar polarizability, and Tc is defined as ferroelectric transition temperature or the Curie's temperature. So students, you can see the ferroelectric to paraelectric transition, which is shown by this figure. The ferroelectric behavior is observed below the Curie's temperature and above which the ferroelectric phase converts into paraelectric phase, which always has higher symmetry than the ferroelectric phase. For example, from tetragonal barium titanate to cubic barium titanate at about 120 degrees Celsius, and the ferroelectricity disappears. A paraelectric phase is a state where dipoles are randomly oriented in crystals, giving rise to zero polarization. Proof of Curie-Weiss law. We can now say that a ferroelectric material reversible spontaneous alignment of electric dipoles takes place by mutual interaction. This happens due to a local field E, which is increased by dipole alignment in the direction of field. This phenomena happens below a temperature Tc when the thermal energy, that is kT, is small enough so that the electric field can overcome the dipole randomization due to thermal vibrations. So we know that the polarization can be expressed as P is equal to epsilon r prime minus 1 into epsilon naught E, which is equal to n alpha E dash, where E dash is the local field, which is given as E plus P upon 3 epsilon naught, which is given by Clausius-Massotti relationship. In the given expression, epsilon r dash is the relative dielectric permittivity and alpha is the total polarizability. On substituting the value of E dash, we get P is equal to n alpha E plus P upon 3 epsilon naught, which is equal to n alpha E plus n alpha P upon 3 epsilon naught. So after rearranging the equation, we get the value of polarization P is equal to after rearranging the equation, we get the value of P as n alpha E divided by 1 minus n alpha upon 3 epsilon naught. Since we know that the susceptibility is given as epsilon r dash minus 1, so it is equal to P upon epsilon naught E. So we get the value of susceptibility as n alpha by epsilon naught divided by 1 minus n alpha upon 3 epsilon naught. So this equation shows that both susceptibility and relative permittivity must approach to infinity when n alpha upon 3 epsilon naught approaches 1. This can be assumed to be right condition for ferroelectrics, as near the ferroelectric transition they exhibit very large susceptibilities and dielectric constant. At this point, we can also ignore the electronic, ionic and interface polarizations, assuming that the dipolar polarizability is too high, such that alpha D is very much greater than alpha E plus alpha I plus alpha int at a critical temperature Tc. Here, alpha is alpha D, which is equal to C by kT, where C is the Curie's constant. And this is right sort of relation, as we have already seen that the temperature dependence of dipolar polarization in the previous sections. Further, we can write that n alpha upon 3 epsilon naught is equal to n upon 3 epsilon naught into C by kT is equal to 1. So, Tc is equal to Nc upon 3k epsilon naught. So below this Tc, the spontaneous polarization is prevalent and the dipoles tend to align. So since C is equal to alpha naught kt, we get Tc as n alpha t by 3 epsilon naught, or Tc by t is equal to n alpha upon 3 epsilon naught. Thus, by now modifying the expression, the Curie-Weiss law can be expressed as susceptibility, that is chi, is equal to n alpha by epsilon naught divided by 1 minus n alpha upon 3 epsilon naught, which comes out to be 3 Tc divided by T minus Tc. Ferroelectric switching and domains. Applications of an electric field to a ferroelectric ceramic leads to alignment of anti-parallel or off-aligned dipoles to reorient themselves along the field. At sufficiently large fields, all the dipoles will be aligned along the field and the direction reverses by reversing the direction of the field. This phenomena of polarization reversal takes place by way of nucleation and growth of favorably oriented domains into the unfavorably oriented domains and associated domain wall motion. So students, you can see this type of behavior in the plot shown, which shows the characteristics of the hysteresis loop of a ferroelectric material, where electric field is there on the x-axis and on the y-axis there is a polarizations. You can see the value of remnant polarizations and the saturation polarizations along with the coercive fields. So if we assume that our hypothetical crystal has an equal number of positive and negative domains in the virgin states, then the net polarization of a crystal will be 0. Now what happens when field E is applied? So the plot that we get something like shown in the previous slide, where P is the polarization in microcoulombs per centimeter square and E is the electric field across the sample in volts per centimeter. The process is something like, we can explain in detail, like in initial polarization P increases linearly with increasing electric field and the crystal behaves like a dielectric because the applied field is not large enough to switch any of the domains oriented opposite to the direction. So this linear region is shown in this module with representation AB. Further, with increase in the field strength, the force nucleations and the growth of favorably oriented domains at the expense of oppositely oriented domains, and polarization starts increasing rapidly until at the domains are aligned in the direction of electric field. That is, they reach a single domain state when the polarization saturates to a value called saturation value. So the saturating curve where the loop saturated, this saturation, if we take a tangent to the saturation line that intersects the y-axis, that point is called saturation polarization. So the domains reversible or the domain's reversal actually takes place by formation of new favorably oriented domains at the expense of unfavorable domains. Now, when the field is decreased, what will happen? The polarization generally does not return to 0, but follows a path which is represented by DE in the loop, and at 0 field some of the domains still remain aligned in the positive direction and the crystal exhibits a remnant polarization. So till now what we have read, that the polarization increases linearly, then it saturated, reaches the saturation polarization, and when we reverse the field, the polarization does not complete goes to 0. It has some polarization, means the domains are still aligned, so they are cutting the y-axis, and that point is known as remnant polarization. So to bring the crystal back to 0 state, a negative electric field is required along the path EF, which is also called the coercive field. So further increase in electric field in the opposite direction will cause the complete reversal of orientation of the domains in the direction of field, which is denoted by the path FG, and the loop can be completed by the following the same path as GHT. So this relation between polarization P and electric field E is called ferroelectric hysteresis loop, which is an important characteristic of a ferroelectric crystal, and the principal feature of a ferroelectric crystal is not only the presence of spontaneous polarization, but also the fact that these polarization can be reversed by application of an electric field. So the domain switching in a previously polarized ferroelectric sample can also be viewed in the following slides. Measurement of hysteresis loop. Ferroelectric hysteresis loops can be experimentally measured using a sawtooth circuit using a high-frequency AC field and are observed on a screen of an oscilloscope. The circuit is schematically drawn in this slide. A linear capacitor C0 is connected in series with the crystal. In this configuration, the voltage across C0 is proportional to the polarization of the crystal. This circuit not only measures the hysteresis loop but also quantifies the spontaneous polarization, that is PS, and coercive field, that is EC. Nowadays, one can get commercially available instrument such as Radiant Precision Station from Radiant Technology, which can perform various polarization measurements at varying fields and frequency. Application of ferroelectrics. In addition to barium titanate, extensively studied ferroelectric material have been lead titanate, lead zirconium titanate, BTO and SRBTO. While first two shows large polarization and a reasonably high Curie's temperature, later two do not have lead and have very high Curie's transition temperature. Although many applications of ferroelectrics are for their piezoelectric properties, ferroelectrics can be used for applications like non-volatile data storage below their TC, whereas at above TC, where their dielectric constant increases linearly with temperature, they can be used for camera flashes. So the first application is non-volatile memories. Since ferroelectric materials show a hysteresis loop and a remnant polarization at zero fields, these two polarization states can be used as 0 and 1, corresponding to plus PR and minus PR states of binary data storage in memory devices. So such states you can see in the plot shown in the slide, where the ferroelectric memory states of plus PR and minus PR are shown. The advantages are that the data will be stored when power is lost during the operation, leading to non-volatile data storage. Other advantages are that the ferroelectric switching is very fast phenomena and hence memories can operate very fast. Many of these materials tends to radiate resistance and hence can be used in space application. However, in camera flashes, in such application, the battery charges the ferroelectric capacitor first, and then once fully charged, the ferroelectric is connected to the bulb and causes it to flash. So students, let us see what we have done till now and what we understood till now in this module. So in this section, we discussed firstly about the ferroelectric materials, which are characterized by non-centrosymmetric structure materials exhibiting a polar axis whose direction can be reversed by changing the direction of electric field. So it is clear that every ferroelectric material are non-centrosymmetric. So these materials also follow a Curie-Weiss behavior, that is a transition from ferroelectric to paraelectric phase upon heating across a Curie's temperature, that is Tc. Moreover, we have read that the nature of phase transition can be first or second order depending on the type of material, which is reflected in the way polarization changes as a function of temperature. So the ferroelectric material, when switched under alternating field, show typical hysteresis-like behavior, showing two stable polarization states, that is plus PR and minus PR. Here plus PR and minus PR are the positive side remnant polarization and the negative side remnant polarization, which are useful for memory application, where these are used as states 0 and 1 for binary data storage. So the reversible of the polarization take place by domain reversible, which is a phenomena happening by nucleation and growth of new domains. And the typical example of commonly used ferroelectric materials are perovskite structure compounds like lead titanate, barium titanate, and even lead zirconium titanate. So lead zirconium titanate is the best example for the PE or ferroelectric materials. So one of the most important application of ferroelectric materials are in non-volatile ferroelectric memories. Besides other application, there are much demand of such type of materials in flash bulbs and sensors, actuators, and so on. Thank you.